All right, folks. Mr. Kuntz here again. We are going to do 2-3 today, which is Introduction to Matrices. And what we're going to talk about with matrices, and matrices is just the plural form of matrix, guys. And yes, just like the movie Matrix, but not just like the movie because this is the math matrix, not a computer matrix that gives you dreams, I think is the whole system behind Matrix, the movie. But anyways, matrix is a rectangular array of data. That's all it really is, all right? We put data into this rectangular box, so to speak, and it's so we can arrange things, and it's kind of the language of computers in a way. When we arrange things in matrices, we can program them into a computer system, but you need to know how matrices work first, and that's where we're going to start, is just the basic math of matrices. And that starts with the language. Like I just wrote down, you see that we are talking about a matrix. All right, when we have a matrix, I'm just going to give you an example of one. A matrix could look like this. This would be an example of a matrix. Let's say this. All right. Now this matrix, when I talk about each of these numbers that's in here, in this array, this is a rectangular array. We use brackets on the end. We don't completely box it in, but it's a rectangular array. By array, I'm talking an arrangement, all right, of data. Each of these pieces are called elements, all right? These elements make up the matrix. So we have elements in a matrix. That's what we talk about, not the numbers in the matrix, they're elements of the matrix, because it's not always numbers. This can be letters, this can be anything. We in math generally use numbers, but in truth, in the bigger, broader scheme of matrices, you can have other things in here besides numbers. All right, and you'll see a little bit of that when we get some of our nice variables in there later on as we get into this today. All right, but first, let's go to some other words. When we talk about matrix, the next thing we're going to talk about is the dimension of a matrix. When we talk about the dimension of a matrix, the dimension is described by the rows and columns. All right, so rows go this direction. Columns, just like on a building, go up and down. All right, so when we talk about the dimension of a matrix, we describe it as rows by the x, like 2 by 4. You put that x between a 2 and a 4 and call it a 2 by 4. We have rows by columns. So when we say rows by columns, like this right here would be a 2 by 3 matrix. 2 rows go in this direction, 3 columns. So this is a 2 by 3 matrix. We always use it in that order, row by column, okay? If we have a square matrix would be something like this. Let's say we just take these pieces and we create a matrix that looks like this. This is a 2 by 2 matrix. It's square because rows and columns are equal. We would call this a second order matrix. When we talk about square matrices, they are of a certain order. If it's a 3 by 3 matrix, it's a third order, okay? So these are just some of the words to get out of the way. Now, another thing I like to do, and it's a little different than your book shows, but I also like to think of matrices in general terms. If we talk about any kind of matrix, one thing we do is we name matrices. And normally when we name matrices, sometimes they're given word descriptions, but generally speaking in math, we use capital letters. So if I called this matrix A equals, it would have elements that are elements of A, the matrix A. Now, when I use this, what I want to show you is how I subscript the elements. If I'm just talking general matrix A, then I use little a for the elements. And let's say I have this kind of matrix. Now, the thing is, it looks kind of silly with all A's, right? These are elements of matrix A, but they have subscripts. This would be 1, 1. This would be 1, 2. This would be A sub 1, 3. Then A sub 1, 4. A sub 1. I'm sorry. I just got carried away. Sorry. Let's do this correctly, and so I don't throw you. This is 2, 1. This is 2, 2. This is 2, 3. This is 3, 1. A sub 3, 2. And A sub 3, 3. Now, think about that for a minute. What do you think those subscripts say? What do they tell us about that element? If I asked you about element A sub 2, 3, what does that mean? That is the element in second row, third column. Just like we talk about dimension, we talk about position. So this matrix, if I look at this matrix, this is third row, first column. Third row, first column, that's that position. All right, so you're going to see this notation showing up quite a bit as we work through these. All right, so again, just some basic concepts of how we describe things, how we talk about them, and you'll get comfortable with this hopefully as we go through some examples. All right, we got one more concept. I'm going to go to a new page here. We're going to talk about when are matrices equal. And I should just write it that way. I'm going to do this. Equal matrices. All right. Matrices are equal when all their elements, let's put it even better than that. They're equal when they have same dimension, and each element is identical. Meaning, if I look at the element in row 1, column 1 in matrix A, and I know that in matrix B is equal, it'll have the identical row 1, column 1 element. All right? When they have the same dimension and each element is equal. And how are we going to use this? This is where we're going to start getting into examples, which is really when you're going to learn about this. I'm just trying to set some background so you can understand when I start talking about these things. So let's look at an example of how we would use equality of matrices. And these are just some basic things we're going to want to be able to do. So for example, if I gave an example that said find the values, and this is where we start using some variables. All right, so find the values of X and Y for which the following is true. All right, and then they're going to give you something like this. Let's see, we'll do this one. We're going to do y plus 4 and y. That's supposed to be a 4. I want that to be clear. And then that is equal to x minus 1 and 3x. So what they've given us here is two equal matrices. It says that they are equal. This is a 2 by 1, right? It's got 2 rows, 1 column. This is a 2 by 1. So they have the same dimension. And if we're told they're equal, we know they have to have identical elements. So what does this tell us? It tells us we have this. It's saying this, here, let me do this in a different color so we get a little bit better perspective on this. This element has to be identical to this element. So in other words, y plus 4 has to equal x minus 1. At the same time, we have to have this element identical to this element. So we know y equals 3x. So knowing these equalities, these equivalencies, and they want us to find the values of x and y, well, what do we have here? We have a system, don't we? We just finished doing systems. This is two variables, two equations, and we've got one solved for y. So can't we just solve this system like we did in the previous sections? Sure we can. Go back. Let's take a look at this. If I know this is what y is, I can plug it into y here and then solve this. So I would get 3x plus 4 equals x minus 1, just using substitution. This is just solving a system of equations. We've already done this, right? So subtracting x from each side gives us, let me get a little more room. This would give us 2x plus 4 equal to negative 1. Subtract 4 from each side, and we'd have 2x equals negative 5. And that would tell us that dividing by 2, x is equal to negative 5 halves. So we've solved for x, so we have one of the things we wanted. We need to find y. Well, how do we find y? Well, what did we know? Up here, they told us y is equal to 3x. So I just go over here and say y equals 3 times negative 5 halves, which is negative 15 halves. And we have our value for y. And we've solved what they asked us to do. They told us in the beginning they want us to find the values of x and y. So we found the values of x and y. You don't have to write these. I know you're thinking system of equations. Do we write this as an ordered pair? You don't have to. They just said find x and y. So we found x, we found y. We're done. All right, but we did that because we know equivalent matrices have identical elements. All right, that's the key there. So now, what else can we do with this wonderful world of matrices? Well, we can also do operations. All right, that's what we're going to look at now, is operations on matrices, or with matrices, I guess might be better. Well, it's kind of with and on, but now I'm just babbling to myself. So hang with me here while I write this out. So operations with matrices. Let's do this. I'm going to give you two matrices, and let's just use some examples. All right, matrix A is going to be this. It is going to be, first off, bigger than that. So I'm going to make a little bit bigger space for myself here. All right, let's do this. A equals. And we're going to let it be 2, negative 4, negative 1, 2, and 3, negative 8. So we have this matrix A, and we've got a matrix B. Matrix B is negative 5 and 7, negative 4 and 8, 1 and 4. And we'll even have a third matrix here. That one is 2, negative 1, 5, 3. So we have these three matrices. Now, they may ask us to do this operation. For example, they may say, find A plus B. What they mean by that, when they say find A plus B, is use these matrices and find their addition. And we can add matrices, but there are a couple conditions. All right, with addition, you have to be sure, the most important condition, I should say, really the only true critical condition, is they have to be the same dimension. If they are not the same dimension, we cannot add them. All right, they have to be the same addition or same dimension to do addition. Now, if they aren't the same dimension and they ask you find A plus B, you just say no solution. Or you can say a dimension mismatch. That's what your calculator would tell you if you tried to do it on a calculator. If the dimensions don't match, you could say that. All right. But for us, when we look at A plus B, well, what is the dimension of A? Dimension of A is 3 by 2, right? 3 rows, 2 columns. Dimension of B, 3 by 2. 3 rows, 2 columns. Same dimension for both of these, so we can find A plus B. And let's do that. Now, with addition, the resultant matrix will have the same dimension. I'll put will be of equal dimension. To the originals, all right? The resultant matrix will be of equal dimension. So when I'm adding A plus B, and they're both 3 by 2, it's the first thing I got to check. They are both the same dimension. The result of this will be 3 by 2. So I need to give myself brackets. That somehow came out rather slanted. But we have brackets. These are going to be, again, 3 rows, 2 columns. That's the result. Now, the rest is exactly as you would hope. I know math often says, this is what it looks like, but we're going to do it this way. This is exactly like you would hope it would turn out. All we need to do to add these, or subtract, which is the same idea, but just subtracting, all we have to do is look at the dimension of each in the identical position. So when I want to do A plus B as a matrix, I do A sub 1, 1 plus A sub 1, 1. And so 2 plus -5 gives us -3 in that same position in the resultant matrix. For A1, 2, A sub 1, 2 would be -4 plus 7. So that's going to be 3 in the A sub 1, 2 position in the resultant matrix. -1 plus -4 make -5. 2 plus 8 make 10. 3 plus 1 makes 4. I almost said 3 there for some crazy reason. -8 plus 4 is -4. And this is our A plus B matrix. So let's use those same matrices. And let's see if we can find, let's see. Oh boy. What I'm going to do is something I don't like doing on these, but I want to stay in the same place. Well, no, we'll just, you know what? We'll do these again. Let's just find new space here. All right, so now I'm going to draw those again so we have them to work with. And that was 2, -4, -1, -2, 3, -8. B was -5, 7, -4, -8, 1, 4, and my memory's failing me now. I'll just make another C. And we have this again. We could also be asked to do something like, let's get crazy with one. We could be asked to do, say, 2A minus B. Now, 2A, what does that look like? Well, 2A is nothing more than matrix A multiplied by a scalar, what we call a scalar multiple of 2. That means every element in A will be multiplied by that scalar multiplier of 2. So 2A would look like this. It would be 4, -8, -2, -4, 6, and -16. And all I did was multiply each one of these by 2. That's my 2A. So what we're really doing is 2A minus that B that we already saw. And B is that -5, -5, 7, -5, 7, -4, -8, 1, 4. And that, again, we look at and say, this is 3 by 2. This is 3 by 2. I can do this subtraction. So my resultant will be 3 by 2. And we just do what it says, 4 minus -5. Minus a negative is adding, we get 9. -8 minus 7 is -15. -2 minus a -4 is +4, so that's 2. Uh-oh. Oh, we got a runaway pen. All right. Sorry. Again, -2 plus 4 is 2. And -4 minus a negative, or +8, is 4. 6 minus 1 is 5. And -16 minus 4 is -20. And this would be 2a minus b. So we can do scalar multiples. We can add, subtract. Let's do another one real quick. Let's do 3b minus 4c. So we could look at this and say, all right, I'm doing 3 times b, this is my b matrix, minus 4 times this matrix. So I'd multiply each of these by 3 and each of these by 4. But before I get that far, I hope all of you are just trying to point out something to me that you can't stop me now because I can't hear you. But if you noticed, this is a 2 by 2, and this is a 3 by 2. So I don't care if I multiply this by 3 and multiply this by 4, there's still going to be 3 by 2 and 2 by 2. So I can't do this. So this is a dimension mismatch. I can say dimension mismatch. You can say, I accept this as an answer. I also accept no solution. What did happen there? Hold on a second. It did not like me going off screen. No solution is another thing to write. Don't say can't do it. That may just be a commentary on your skill. So don't say can't do it. Say no solution, dimension mismatch. Let's talk mathematically. All right. Or the dimensions don't match. I would accept that. All right. So that is our operations. Those are our addition, subtraction, multiplication type of operations with these matrices. Now, the one thing we didn't talk about, we got one thing left, and this is going to take a minute. All right, we have one thing left, and that's multiplication of matrices. And I know this is getting a little long, so if you feel like taking a break before you get into this, hit pause and wait. But this is the last thing we're going to go over. Let's do, again, a couple different matrices. Let's do 3, -2. I like to use examples for this, guys, to show how to do it. We've got this and this. All right. If we wanted to do this operation, AB, that means this times this. I want to be really clear right from the beginning because we don't have time to investigate this a little more in class. We will later, but I want to be clear to you that AB is different than BA, and you should see why. We're going to do both of those at some point here, but I want you to see this as we go through it. The way we do this multiplication is we again look at their dimension. We have a 2 by 2 times a 2 by 2. Now, what we want to do, we first have to do the same thing we did with addition and figure out whether we can do this. And the way we figure out whether we can do this is we look at, in order when we draw these, if we put these matrices in order of multiplication, we take the column from this one and the row from the second one. If these match, then we can do this multiplication. If they don't match, then again, you say dimension mismatch, and you are done. When I say they match, they are equal. All right, they are the same number. You have the same number of columns as you have rows in the second one. Columns in the first, rows in the second. All right, and this number will tell you the dimension of your resultant. So our resultant is going to be, in this case, 2 by 2. So this is going to be equivalent to a 2 by 2 matrix. So that 2 by 2 matrix is going to have an A11 element, an A12, an A21, and an A22 element. Now, the trick is finding those. All right, once we have this set up, what I want you to do, whoops, not that, is draw yourself this matrix again. We're going to fill in the numbers that are going to take these places. And we're going to do this by doing operations. All right, now this is what we're going to do. When we do this, this first position, this one right here, A11, I'm going to look at, we always talk about dimension as row by column. This is why the rows and columns have to match in these two things, in this middle way. Row by column. All right, row by column is how we multiply. So when we do this, I'm going to be doing the first element in this row times the first element in this column. So I'm doing 3, A11 is going to be equal to 3 times 2, and then we're going to add the second element times the second element. So negative 2 times 4. So this is equivalent to 6 plus negative 8, or negative 2. That is our A sub 1 element. All right. So again, A11 told me I'm doing first row, first column. Now, when I want to go to first A12, I go first row, second column. So now let's do that. Let's look at finding A22, or I'm sorry, A21. A21, A12. I'm trying to look at one thing and do another. I'm sorry, guys. A12. A12 is, again, first row, second column. So I'm going to do first element times first element, 3 times negative 1, plus second element times second element, negative 2 times 6. And that's going to be negative 3 plus, what is that, negative 12. So that is going to be negative 15. So next, let's get another color. We need to do A21. So what do you think we use? A21 would be here, right? A sub 21. So now we go second row, first column, and we combine those elements. Negative 1 times 2 is negative 2, plus 4 times 5 is 20. This would be 18. All right, I'm going to give you a minute. I want you to try doing A22. I'm not really going to waste a minute. I'm going to let you pause. Try pausing, do it. All right. And now by the magic of video, we're back. So what do? When we're doing A22, second row, second column, first element times first element gives me positive 1, plus second element times second element gives me 30. I get 31 there. And we have our resultant matrix. Okay, let's do one more. Last one, last example. And I'm going to run through this at real-time speed now. If I give you matrix A, that is, let's say A is, well, let's just use the same one, 3, negative 2, and negative 1, 5. And B is equal to, let's say, oh, what are we going to use? Let's do 0, 1, 2, negative 4, 3, negative 2. And we want to find AB. So if we want to find AB here, we know this is 2 by 2, and this is 2 by 3. So if I look at them in order, A times B, these match, so we can do it. The resultant is going to be 2 by 3. So AB is going to be equal to something that looks like this, where I'd have A11, A12, A13, A21, A22, and A23. And we can find out what those are. All right, so what is that going to be? That's going to equal, let's start getting ready to fill these in. A11 would be first row, first column. See how they match up? They're each 2 elements. 3 times 0 is 0. right? So A11, and we're going to ask you to write your workout for this, guys, just like I'm doing here, just some basics. 3 times 0 is 0, plus -2 times -4 is 8. So A11 is 8, and I can put that in. Then I can go and do A12. So 1 and 2 gives me 3 times 1. So A12 is 3, plus -2 times 3 is a -6. That gives me overall -3. Now, I can go to the next A13, and let's just use that. All right, so A13 would be first row, third column, and I would do 3. Let's write it down. A13 is 3 times 2, or 6, plus -2 times -2, or 4. That is 10. We have that done. Now we can go to the next row. Looking at this, we know we've got to do A21. So A21 is going to be second row, first column, and that's going to be -1 times 0, or 0, plus 5 times -4, that's a -20, and you get -20. So -20 is our A21. We get another color. All right, so now A22. A22, second row, second column, -1 times 1 is -1, plus 5 times 3 is 15. That is 14. We got 14 there. Last row and column, last position, 2, 3. So A23 equals second row, third column. So -1 times 2 is -2, plus 5 times -2 is -10, and that is -12. Now, went through that kind of fast. Hopefully I didn't mess up any arithmetic there. I don't think I did. Again, if you take this kind of approach, it does eliminate a lot of the errors. So we have AB. What I want to ask you, is it possible to do B times A? Well, B times A would be a 2 by 3 times a 2 by 2. And so when we do this, there's a mismatch, and you'd have to say dimension mismatch or no solution, right? So A times B is different than B times A. Sometimes one exists and one doesn't. Sometimes they're just different sets of numbers or they're different sizes. So you have to be careful. What you can do is in terms of order. All right, order is important in these multiplications. And I think I'm just going to stop there because that was an awful lot for one day. So get to work on some of the exercises with these, and we will handle questions tomorrow. Have a wonderful day. All right.